In a previous video, we talked about the flux formulation in the cell Tn to Tn plus 1, and we reached at the following flux. When we have u bar greater than 0, the flux at I minus 1 half is written over here. When u bar is less than or equal to 0, then we have a flux defined over here. Now the idea is we don't want to connect flux with the slope. We know that changing slope means we get different answers. When we have, for example, sigma and the slope is equal to 0, then you get upwind method. Very simple. But if you change this sigma and I minus 1, it depends what we have what you consider u bar. Then replacing this slope with other formula, you get, for example, Lex-Vendroff or beam warming method. So the idea for flux limiter is the flux limiter, there are two terms. One is the slope limiter. Slope limiters mean you just work in slopes. Flux limiters mean we will see how this will be replaced with some other variable. Okay. So we do not associate sigma with flux in the flux limiter. We know that the jump across the interface, for example, we have a jump Qn I minus Qn I minus 1, that will be equal to delta Q n I minus 1 half. This is the basic thing that we know that you can define. Okay. For example, we have, this is I minus 1 half, and if you want to measure the change in I minus 1 half, you measure it, for example, this is I minus 1. So you take a difference of Qni with Qni minus 1. Then you get delta Qni minus 1 half. So if we consider slope only, then this will be divided by delta x. Then this becomes sigma ni or I minus 1. It depends what is u bar. Okay. Rather than writing flux in this piecewise construction, let me write this in one formula where we can cover these two functions in one equation. Suppose we have Fn I minus 1 half. This is the flux at I minus 1 half. Either u bar is greater than 0 or less than 0. What we can do, we take u bar, which is constant, and negative sign. Let me just emphasize with some another color. It is negative. And for negative, we have Qni plus. Then we have u bar, speed of wave. Now we consider plus sign. Plus means u is greater than 0. Then we have Qn I minus 1 plus, we need to make it a general statement, general equation, which covers both. So in this case, if I want to write plus over here, then this u bar can be positive or can be negative. So we can write 1 by 2, and this is u bar mod, and we have delta x minus u bar delta t, and finally we have, for example, it depends what is over here. We have, for example, sigma ni minus 1/2. Okay, or maybe it is sigma. So it depends what we want to write over here. It can be, for example, delta q n I minus 1/2 divided by delta. So it should be sigma n I minus 1/2. Okay, I just want to manipulate this further. Maybe just I want to discuss it further first. Suppose you have u bar is greater than 0. If u bar greater than 0, then you get u plus will be equal to u bar, and u bar negative will be equal to 0. So we have fn I minus 1/2 is equal to, and this will be 0 when we have u bar greater than 0. This becomes u qn I minus 1 plus, since u bar is greater than 0, so u bar mod will be equal to u bar. We get plus 1 by 2 u bar delta x. Since it is greater than 0, so we have u bar delta t, and then we have a definition of sigma n I minus 1. So from here you can decide, since it is delta x, so you have to decide this sigma n I minus 1/2, which value you want to take. Here in this case, u bar greater than 0, it will be sigma n I minus 1. I hope you got the point. You can just do exercise that when we have exercises, check or find the formula, check fni minus 1/2 for u bar is less than 0. Okay, I just need to modify that as well. We have fn I minus 1/2, that will be equal to u bar negative. Maybe I just copy that since I require that over here. So copy and I paste over here. This is the same term. The only thing I need is I need to take a common delta x from here. So when I take a common, we have 1 minus u bar delta t by delta x mod, and this sigma n I minus 1/2 divided by, it will become delta x. And we already saw that, or maybe I just have to replace this with delta qn minus. I think I should write it with delta qn I minus 1/2. When I take delta x common, sorry, there is some error. It should be delta ni minus 1/2, and when I take common, so it should be look like this, and then I have delta ni minus sigma. It is sigma n I minus 1/2, and we have delta x sigma n I minus 1/2. So these terms remain the same. The last term, this one, I just call it delta n I minus 1/2. So how this works? Why there was a confusion? Since I should not have divided sigma n by delta x. Sigma n I minus 1 half is the slope. It depends whether we have q n I or q n I minus 1 divided by delta x. When I multiply these two with delta x, you get is equal to qni and qni minus 1, which is actually delta qni minus 1 half. And the left hand side, rather than calling it delta qni minus 1 half, when I change that, we get different methods. So I will call that delta ni minus 1 half. So this will be replaced. This will be replaced with delta n I minus 1 half. So what is delta n I minus 1 half? Delta n I minus 1 half is the limited version. It is called limited version of delta q delta q n I minus 1 half. For example, if delta n I minus 1 half will be equal to, if delta n minus I minus 1 half will be equal to delta q n I minus 1 half, you will get Lex-Van method. So changing the slope means we get different methods. So for flux, we replace with this delta n I minus 1 half. Okay. So variation in delta gives you different numerical method like Lex-Van or so on. So this is a modification. It's a kind of modification in delta q n I minus 1 half. So when you change that, you get different numerical method. So rather than calling it delta q, we can develop many numerical methods by changing this delta n I minus 1 half. Okay. So if it is changing constantly, we can write delta n. Now we are moving towards the flux limiters. Delta n I minus 1 half, delta n I minus 1 half will be equal to delta q n I minus 1 half. When it is exactly equal to this value, then we have a particular numerical method. For example, we can get Lex-Van method. So while choosing delta n I minus 1 half, we get different numerical method. If I introduce some parameter, some kind of function, it is not a kind of parameter, but it's a function. If I introduce this function over here and it is a function of theta n I minus 1 half, theta n I minus 1 half, and delta q n I minus 1 half, then this delta can be modified due to phi. For example, let me just take a look at very simple example over here. Suppose that phi is equal to 0. So it means that delta n I minus 1 half will be equal to 0. When delta n I minus 1 half will be equal to 0, then this term will be equal to 0. So you will only get the flux of this form, and ultimately you get the upwind method. Okay. This is the form that we use when we have both u bar greater than 0 or u bar less than 0. It works both ways. Okay. So it means that we introduce this phi over here. And what is this theta? This becomes interesting. We have theta, some people call it r. Some people call it, for example, phi of r. It can be phi of r. So this theta will be equal to change in Qn capital I minus 1 half divided by delta Q n small I minus 1 half. So it means that this is just a ratio of the value change in value, for example Qn I minus Qn I minus 1 divided by, and we have Qn small I minus Qn I minus 1. I repeat again, if you see the value somewhere, this some people call it R and they define it differently. In that case they may call it U and I, so on. So the value of I depends on if U bar is greater than 0, then we have I minus 1. If U bar is less than 0, then we have I plus 1 over here. So that's what we did for the formulation of uh, flux limiters. When you practice it, it's a new thing. If it is a new thing for you, you can just practice and check the things online as well, maybe some other videos. You will understand it completely. So here, as I told you earlier, if I take phi of theta equal to 0, then you get delta n I minus 1 half is equal to 0. It means you get flux n I minus 1 half. Then you get the upwind method. If suppose I do write phi of theta will be equal to 1, then we have delta n I minus 1 half will be equal to delta q n I minus 1 half. When you put that value into your flux, you will get Lex-Van method. Try it yourself. Take the value of this delta q n I minus 1 half and the flux at I plus 1 half, you will find out, you will get Lex-Van method. I hope you get it, the answer. So it means that this phi is crucial over here, since it gives you different methods when we change the limit, when you change the value of this flux function. Okay, this theta is actually called the measure of the smoothness in the data. Smoothness in the data. Okay. Suppose we have, for example, something like that. It is just a ratio of slopes, different slopes, variations only. Since in the numerator we have variation in Q, here we have variation in I. So it is the ratio of these two variations. If the variations are smooth, it just measures that. Okay. Right. So we already discussed that what we have when phi is 0, what we have when phi is 1. Now, particularly, if I say, for example, phi of theta, if we just pick that phi of theta will be equal to theta, then we have delta n I minus 1 half, that will be equal to delta q capital I minus 1 half divided by delta q small I minus 1 half. And if you put this phi over here, maybe I copy that from here, copy, paste. So for example, this is delta. When we have phi of theta is equal to theta, this is only theta. theta is I minus 1/2, and theta I minus 1/2 is uh, defined as follows, and this is delta Q n I minus 1/2. This value over here, you can see that some term will be cancelled out, and we can get delta Q n I minus 1/2. So delta n I minus 1/2. So phi of theta is equal to theta gives you some method over here. And this is the upwind method when we have this is the upwind method. Okay. If you want to find the From's method from this choice, From's method. For From's method, you can define phi of theta is equal to 1 by 2, 1 plus theta. So phi of theta, when you put phi of theta is equal to 1 by 2, 1 plus theta, and you put that value over here, delta n I minus 1/2, that will be equal to 1 by 2, 1 plus theta n I minus 1/2 delta q n I minus 1/2, and then you put the ratio of value of theta, the value of theta you can put over here. Then after some manipulation, you will get the From's method. You can verify it yourself. If we have phi of theta is equal to 2, for example, then we have delta n I minus 1/2 2 delta q n I minus 1/2. And phi of theta with the value of 2 theta, this gives you the jump in upwind interface. So we saw that when we have phi, when we introduce phi in the calculation, then we have in the formula, then we can retrieve different numerical methods. So in summary, I can write it as follows. In the summary, we have, for example, linear methods. For linear methods, we already saw that when we have phi of theta is equal to 0, then you will get upwind method. When we have phi of theta is equal to 1, then you will get Lex-Van method. When the value for phi of theta is equal to theta, then you have beam warming method. When we have phi of theta is equal to 1 by 2, 1 plus theta, and we have From's method. So these are the methods. These are not flux. These are not the limiters. How these can become a limiter? High resolution limiter. How these becomes limiter? High resolution limiters. So for min mod, the phi of theta will be equal to min mod 1 comma theta. If min mod chooses from 1 and theta, then we get the min mod limiter. This is min mod limiter. If phi of theta will be equal to the maximum from 0, min 1 comma 2 theta, and then we have minimum from 2 and theta. Then this is called Spurby limiter. Spurby limiter. Suppose we have phi of theta is equal to max 0 min minimum, which shows minimum. If it chooses 1 plus theta divided by 2 and 2 comma 2 theta, then this is called the MC limiter. And if we have phi of theta is equal to theta plus theta mod divided by 1 plus theta mod, then this is called Van Leer limiter. Van Leer limiter. The V is small over here. Van Leer limiter. So previously we saw that, one short comment, when we have, for example, min mod limiter, the min mod limiter was connected with the slopes sigma n and sigma ni minus 1/2. Okay, so that was a limiter as well, but it was connected with the slopes. Here we connected with the min mod and other limiters with theta. It has other advantages. It has other advantages. Okay, so this was all about the limiters, and these limiters are mostly TVD, total variation diminishing. So when we have some jump, if you apply, for example, Spurby limiter, then you will get very good comparison. Previously, we saw that if we had only Fromm's method or beam warming or Lex-Van Roff, there was oscillations. Now these oscillations will be removed if you choose min mod, for example, Spurby, MC, or Van Leer limiter. That is the main thing in this research. Thank you for watching.